I'm Dr. Andrea Strzelik, and this is Problem Solving for Thermodynamics. Before I get going on calculating an example problem with you, the first thing I want to do is go over the problem solving steps that I'm going to use to approach the problem. Step 0, and it's 0 because you can't even begin to solve the problem until you know what it's about. So step 0 is to read the problem carefully, identifying keywords and information. When I'm reading the problem statement, I like to do it with a pencil in hand so I can underline the keywords and the information as I encounter it. It keeps me from missing things and makes it less likely that I will forget to use some key information in the problem statement. Once you've read the problem and you know what it's about, step 1 is to make a note of what you're asked to solve. It's really often useful to list what you need to find, and many thermodynamics textbooks explicitly request that you write down what you're asked to find in the problem. Step 2 is to draw a diagram or some kind of schematic of the problem. It's useful to label it with key information from the problem statement. This is your underlined information, and just to help you to keep track of what's going on. In step 3, you should identify what kind of system you're dealing with. For example, is it open or closed? Is it an ideal gas? Or is it a liquid or a solid? Or is it something undergoing a phase change? This identification is really important because it will help you determine which form of the governing engineering models you're going to use, how many balances you need, and also where you're going to get your property information, whether you're going to be using the ideal gas law or looking things up in the property tables. In step 4, you're going to write the key engineering model or models that you will use to solve the problem. And in step 5, you're going to explicitly make a list of the assumptions that you're making or properties that you're going to put into the equation written in 4. Step 6 is to simplify the engineering model based on 5. Something that's really key is trying to keep your calculations symbolic as long as possible. I've often seen students make mistakes or waste a lot of time on an exam because they are calculating a quantity they really didn't need, and if they had kept their equation symbolic, they would have realized it canceled out in the equation or across the equation. In step 7, we're going to substitute numerical values and units, very important, into the model. Sometimes using units seems like a bit of a pain. However, that extra few seconds it takes to write them down can often make the difference between successfully solving the problem or not. And in step 8, we're going to calculate, and we're going to make sure we calculate everything that we've identified in step 1. And then probably most importantly, in step 9, we're going to do a sense check. We're going to make sure the value and the units that we calculate make sense and match what we're asked for. Okay, let's do an example problem. So step 0 is to read the problem and identify keywords and information. This is problem 2.67 from the 8th edition of Moran Shapiro, Bettner, and Bailey. The problem states that we have 4 kilograms of carbon monoxide contained in a rigid tank with a volume of 1 cubic meter. The tank is fitted with a paddle wheel that transfers energy to the carbon monoxide at a constant rate of 14 watts for 1 hour. During the process, the specific internal energy of the carbon monoxide increases by 10 kilojoules per kilogram. If no overall changes in kinetic or potential energy occur, we're asked to determine the specific volume at the final state. Remember, specific volume is the total volume divided by the mass, and we're asked at the final state. The energy transfer by work in kilojoules, so we're looking for work. And then we're looking for the energy transfer by heat transfer in kilojoules and the direction. And so the direction will depend on the sign. Remember, if we get a plus, that means heat is being transferred in, and if we get a negative number, that means heat is being transferred out. Okay, so we know what we're asked to find. We're asked to find the specific volume at the final state, the energy transfer by work in kilojoules, and the energy transfer by heat transfer in kilojoules and its direction. Let's take a minute to make a drawing of what's going on. We have a tank which has a paddle wheel. The tank has 4 kilograms of CO. The tank is rigid, so that means the volume is constant. So the initial volume equals the final volume, constant. We know that the paddle wheel is doing work on the CO, so there's work going into the system. Which means the work will be negative. Remember, when work goes into a system, it's negative, and when it comes out, it's positive. Okay, so let's identify what is our system here. Our system is the CO in the tank. It is worth noting that CO is an ideal gas, in case we need any properties. And there's no carbon monoxide going in or out of the tank, so this means we have a closed system, which means it simplifies our mass balance. That means the mass at the initial is equal to the mass at the final. So the change in mass of our system is equal to 0. A closed system also means that when we write our energy balance, we know that the change in total energy for this process has to equal 0. We know that the change in total energy is equal to the change due to the transfers, Q and W, heat transfer and work. And we know that the total energy change is equal to the change in the forms of the energy, delta U plus delta KE plus delta PE. Putting all those things together, we can write that energy transfer by heat minus energy transfer by work is equal to the change in internal energy, and that's total internal energy, plus kinetic energy plus potential energy. So now let's make a list of assumptions as we approach the problem. We've already made one, and that's the tank is rigid and that the volume is constant. We are also told in the problem statement that the kinetic energy and the potential energy can be neglected. So if we use that to simplify our problem statement, we can cross out KE and PE because we know that they're both 0. We're also told that the work going into the system is 14 watts, which is a rate. A watt is a joule per second. And we know that there's a change in specific internal energy of 10 kilojoules per kilogram. So now let's look at the things that we are asked to find. We're asked to find the specific volume at the final state. Specific volume is the total volume divided by the mass. Well, we know that the tank is rigid. We know that the system is closed. So if we're asked to find the specific volume, total volume divided by mass, We know that the total volume is 1 cubic meter and the mass is 4 kilograms. So the specific volume is 0.25 meters cubed per kilogram. Next, we're asked to find the energy transfer by work in kilojoules. We know the rate of energy transfer into the system in watts, but watts is a joule per second. We also know that the paddle wheel runs for 1 hour. So, for part B, we're looking for work. Work is equal to the rate of work times the duration, which means that this is 14 watts, and we know that there is 1 joule per second per 1 watt, times the time, which is 1 hour, but you can see we need seconds in order to get to joules. So there are 60 minutes in 1 hour and 60 seconds in 1 minute. So in the end of this, you can see that my hours will cancel, my minutes will cancel, and I'll be left with seconds. So calculating this, we see that we have 14 joules per second times 3,600 seconds, and that's 50,400 joules. It's also important to note that this is work into the system, so our work is equal to minus 50,400 joules because the paddle wheel is doing work on the system. Now, if we go back to our problem statement for a minute, we notice that we're asked to find the energy transferred by work in kilojoules. So if we go back down, you can see here that we actually right now have joules. So work is minus 50,400 joules times, there's 1 kilojoule for every 1,000 joules. So we end up with minus 50.4 kilojoules. And that's our answer to part B. Now the third thing we're asked to find is the heat transfer energy and what the direction is. And we've already got this governing equation. So let's see, let's write that again. Part C, we know that Q minus W, which we've solved for, equals delta U. We know that W work equals minus 50.4 kilojoules. And we know that the change in specific internal energy given in the problem statement is 10 kilojoules per kilogram. In order to find delta U, we know that we have 10 kilojoules per kilogram times 4 kilograms that were in the system, right? Because the total change in internal energy is the change in specific internal energy times the mass. So we get that delta U equals 40 kilojoules. When we put our values into the equation, we see that Q minus W equals delta U, or Q minus 50.4. See, this sign is really important, and that's equal to 40 kilojoules. So what we're able to solve for is that the heat transfer is minus 10.4 kilojoules. So we've now solved for the amount of energy transferred by heat in kilojoules, which we're asked for in part C, and we've solved for the direction because we know that if it's a negative number, the heat transfer is going out of the system. Remember, work in is negative, work out is positive, and Q in is positive and Q out is negative. Thermodynamics came from a desire to turn heat, thermal energy, into work. So Q going in is positive and work going out is positive. So our sense check, did we solve everything we were asked to? Yes, specific volume, and that makes sense. And those are the correct units for specific volume. The work we were asked to solve in kilojoules, it makes sense, and negative because the paddle wheel does work on the carbon monoxide. And then in the third part of the question, we were asked to find the heat transfer in kilojoules. We solved that to be negative 10.4 kilojoules, and that makes sense that heat is going out of the system.